Hello everyone. My name is Nikhil Anand. I am pursuing my BTech in mining engineering from IIT ISM Dhanbad. Currently, I am in my final semester. Also, I have been teaching as physics faculty at Career Point Dhanbad, IT, JEE and NEET aspirants physics. So, we will today discuss surface tension. I will explain you what is surface tension. Have you heard this name before? Even if you haven't heard this, can you see these beautiful dew drops on my screen? Surface tension is behind them also. We see surface tension all around us. I think you have noticed it or might have not have noticed it. We see all around us. I will do an experiment in my room, which I have already recorded a video. I will play it for you. I have recorded it. First see it, and then we will discuss these boring lectures about what is surface tension and equations. First, let's see this interesting video.
This is the experiment I was talking about. We have taken two different water. One is tap water and another is tap water mixed with soap solution. We have tried to float safety pin on both these solution or water, you can say. So you can see that safety pin is able to float on this water. I will blow some wind to make sure it is floating. You can see it is floating. Now we will try to do the same in this soap solution. We will try. We failed. We will try again. Again, it is not able to float. Why this is happening? Why the safety pin is able to float in tap water in the first place? It is not because of buoyancy. Because if it has been buoyancy or rho Vg as we say it, so then the rho or density of the soap solution is almost similar or even higher than the water solution. The safety pin would have been easily able to float in the soap solution, but it is not able to do so. Why? This is because of surface tension. It is a property of fluid which we will discuss now.
Did you see that? The safety pin was able to float on the tap water but not on the soap solution. When we zoom in, the safety pin appears like this at the surface of water. It is not going down in the tap water, but it has just sank in the soap solution. That is because of surface tension. We will discuss that. First, let's talk about what is surface tension and why does it appears. And these are other examples of surface tension. The insect is able to walk on the water without sinking due to surface tension. Can you see this? There is a depression in the liquid created due to his legs or whatever you can say. This paper pin is also able to float. The same reason behind this. So we will explain these phenomena. Before discussing surface tension, let's discuss what's the difference in the surface and bulk of the liquid. The surface of the liquid is entirely different thing than the bulk of the liquid. What does this even mean? This means that, see this water molecule here. Can you see this water molecule? And this is inside the surface. And this water molecule, it is at the surface only. This is the surface, no? This is the surface. This water molecule is at the surface. This is below the surface, yeah, or inside the surface or bulk of the matter. Can you see there are forces acting from all sides of it? The water molecules inside the bulk of liquid, the forces are acting from all the sides. But that's not the case in the liquid droplet or liquid molecule which is at the surface. Can you see? Forces are acting from this side, this side, this side, but not from above. So there is disbalanced force here. The resultant force is acting towards downward. What you can say, this unbalanced or this what the net force that is being This unbalanced force is responsible for the surface tension. How? Within the body of water, I will read this line. Within the body of water, attractive forces are acting on a water molecule, are pulling in all directions, so cancel out. You can see that, yes. On the surface, however, molecule feel attracted from inside, but none from attractive force from inside. Here only attractive forces from inside, but none from outside. This causes outer molecule or outer layer of molecule to act like a stretch membrane. It is acting like that. Can you see this rubber band here? It is the same is happening for each and every water molecule present at the surface. It is being stretched from both the sides. It is being stretched from both the sides like this only, rubber band. So it is the surface of water molecule has entirely different properties than bulk of matter because the every molecule on the surface is acting like a stretched membrane. Now we can discuss the definition of surface tension. The tension of the surface of liquid caused by attraction of particle in surface layer by the bulk of liquid which tends to minimize surface area. We saw that no? Every molecule inside the liquid like this, suppose this is surface, here is molecule, every molecule inside is pulling this from this side, that side, from everywhere. This side, it is pulling, it is acting like a stretched membrane. Same is written here in another way. Surface tension is the property of free surface of a liquid at rest to behave like a stretched membrane. It is behaving as if the rubber band is being stretched from both the sides. Now, this is normal theoretical definition. We need to quantify it, have some equation. So, surface tension can be defined as the force acting per unit length perpendicular to. I will explain you what this means. Draw an imaginary line like AB on anywhere on the surface of water. Remember, it is on the surface, not in the bulk or inside the liquid. Not. It is on the surface of water. The forces are acting from this side, you can see. And this line AB is not acting like a membrane, which is being stretched from both the sides. Like this only, from this side also, from this side too. Then, if suppose if total forces that is acting on this imaginary line, the total stretching forces that is acting on this imaginary line, let's say it's F. So we define surface tension E and the length of this membrane, this length only. This length is L. Suppose this length is L and the total stretching force on it is F. Then we define surface tension as T is equals to F by L. You can see if the F is the force acting on L length of the line AB, then surface tension is given by F by L. Obviously, its unit will be Newton meter inverse because force unit of force is what? Newton. Unit of length is meter. So Newton by meter or Newton meter inverse will be its. Now we will be able to easily explain why the safety pin float on the tap water. This is what we saw in our experiment. We were floating the safety pin on tap water and soap solution. This is what it appears on the tap water and it just sank in the soap solution. Can you see the both length of the safety pin is like a needle only? You can see here, if you put a needle on the water surface, I had only safety pin in my room, so I did not use needle. Otherwise, it is much easy. So this, both the length of this safety pin is like just a needle. If you put a needle on the glass, this will appear. So we can say that safety pin and needle both are floating due to same reason. for just simplicity, actually needle is for FBD of needle. We will draw force free body diagram of the needle. It is much easier to understand than the safety pin. So we will use the needle to explain what happened to the safety pin. So let's see that. Why did needle float even though it is denser? Density of iron is obviously much more than density of water, but it float. Is it because of buoyancy or surface tension or both? First, see here, observe here that the needle is above the water surface. Needle, no part of needle is underwater. I will zoom in. No part of needle is under the water surface. So there must be no buoyant force. There is no buoyant force as the needle or safety pin has not penetrated inside the surface. It is on the surface only. No part of needle is underwater. So there would be no buoyant force. Then only surface tension can be responsible. I have drawn the zoomed in version of the side view of this needle. Look from this side. It will appear like this. Can you see this? The corner of the needle will appear like this from this side view. This is the water. This is depression created in the water. I have drawn free body diagram of this over here. Can you see? So what happens is that what we just saw, any imaginary line on the surface is being pulled from both sides like this. Can you see? I will erase these red marks. Can you see it is being stretched from both the sides? Same is happening with the needle. When we put needle, it is being pulled by water molecules from both the sides of water. I am drawing this here. Can you see these red lines, red force lines I have drawn here? Same is happening with the needle. Needle is being pulled by water molecule from both the sides like this. Actually, it is not flat because the needle has created a depression. So this force will appear like this. So this is the free body diagram of the force are acting here and here, the both surface tension forces. And surface tension would be equal to T into L. We saw that, no? We defined F is equal, T is F by L. So F would be T into L. The surface tension force acting would be T times L. And here it is acting on both the sides. Here, suppose this is T and let's say L. TL is acting here and TL is acting here also. But we have to balance out mg. We want to see who is balancing mg so that it is not sinking. So this is F, this is F. We will go F cos theta. The component of F, both the forces here are balancing this mg. And we will add both the forces in upward direction in y-axis. Break the components, F cos theta, F cos theta. So FST is T into 2L cos theta. F of surface tension or the component of surface tension which is balancing mg is T into 2L cos theta. Component of these two forces of one force is Tn cos theta, both forces is 2Tn cos theta. And it will balance out mg. Mg is equals to 2TL cos theta. So this force is responsible for the floating of this needle above the water surface. Actually, it's not floating. In general, we use floating terms like a part of some of our object is inside the liquid, which has displaced the liquid, and rho Vg is buoyant force acting. So we say it is floating or floating above the surface, floating inside, floating half sinking. But here is not the case because the object or our needle has not even penetrated the surface. It is just above the water surface. It is no part of it is inside. So what force has balanced it then? The surface tension. Can you now think about it? But why did safety pin sink in soap water, not in tap water? Why? Because what happens is soap decreases the surface tension of water. So what are our surface tension force? F is equals to T into L. F is equals to T into L. If soap decreases the surface tension, it means T decreases. So F is equals to T into L decreases. So total resultant force in the upward direction, that is T to L cos theta. If T decreases, this force will decrease. So it is not able to balance out mg. That's why the safety pin sank in the water. Now you get it? We have time limitations here, so I will just cover this part in much only in this video. There are other topics related to surface tension. I will take these lectures in the next video. These are cohesive and adhesive forces, capillary, contact angle. After completing these topics, whole syllabus of class 11th will be finished. Okay. But first, let's discuss some question based on what we have studied. So, first question is, water surface tension can be reduced by? You just pause the video and think about it, okay? Water surface tension can be reduced by dissolving common salt in water, lowering water temperature, adding detergent to the water. We know adding detergent to the water for sure. Rest we will study in the next topic, then we will discuss. For now, answer is C, adding detergent to the water. If it would have been, for now, just take adding detergent to the water. We just saw adding soap or detergent decreases the surface tension. That's why we are able to wash dirt off using soap solution or detergent, but not with the just tap water. Now moving to the second question. Can you see that raindrops are spherical in shape because of? This is because I told you, the dew drops or raindrops, everyone are in the shape of. These drops are spherical because of surface tension only. So answer would be B. This is a numerical question. Just think about it. It is just based on the FBD we draw earlier. Please pause the video and just think and try to solve it. Now I am proceeding to the solution. Just pause and think. This is very easy. It might appear very difficult to some, but this is very easy. Okay. This is the solution. Can you see this water molecule? This thin wire, surface tension will act like this here and here also. Same as we saw in the needle. Surface tension will act here and here. Like this. And if this wire is not moving in the y direction, what are the forces acting? This is mg. And this is surface tension force, which is equal to TL. You can see that TL here. And if we take if we divide this TL into two components, so on this side would be TL sine theta. On this side TL sine theta. It will cancel out, and 2TL sine cos theta will be equal to mg. The question is asking us to find the surface tension. We can easily find it. Why? How? Can you see there is a triangle here? This triangle here only. Wait, let me erase these lines. Can you see this triangle here? Just try to find the cos theta in it. You will easily get what is cos theta? B by h. So by cos theta is y upon root under y plus a square, root under y square plus a square. For y less than a, I will explain this, okay? See, why it has written y by root under y square plus a square as y by a. Suppose if y is less than, suppose y is 10, suppose y is 10 and a is 0.001, 0.01. If we square it, it would be 100. And what it would be? 10 to the power minus 4. So it will be almost equal to 100. No, if y a is less than y, so if y is less than a, then one term will be obviously negligible in comparison to other terms. So we have written cos theta is y by a, and now just write it in the equation. And what would be mg acting? If length per unit length is lambda, if mass per unit length is lambda and length is L, so lambda Lg will be equal is what mg is. Lambda Lg, what is mg is. Okay. So we have just equated these two terms. 2TL cos theta is equals to lambda L into G. 2TL cos theta into lambda L, just rearrange the equation, you will get the value of T. So for now, this video is over, but there are other topics also, capillary actions we will study in the next video. Thank you.